Okay, so we are looking at thermal expansion in solids. Okay, now there's a part 1 of this video on how the values for L and T are obtained. Okay, we are looking at the theory side. Okay, now this is the formula for thermal expansion in solids. This is the formula for thermal expansion in solids. Okay, now this is the change in length, okay, of the solid. This is the change in temperature. This is the coefficient of linear expansion, okay, and then this is the final length of the solid. Okay, now after that we can call this equation 1, right? Now we agree that to get the change in length of this metal bar, if we call this pen our metal bar, and we apply heat to it, temperature, okay, to it at a constant temperature, at a constant pressure, okay, we agree that the change in length should give us the final length minus the initial length. Okay, we can call this equation 2. But this is proportional to the change in temperature. The final temperature minus the initial temperature, right? So we can call this equation 3. We said this is the equation for thermal expansion in solids. Okay, now for change in length, it should give us the final minus the initial, which is proportional to the temperature. Now this can be related to Charles' law, which tells us that the volume of a gas, right, is proportional to the temperature at a constant pressure. Okay, so we are not really making use of the pressure here, but this time around we are finding the thermal expansion in solids, not gas. So we are not applying Charles' law, but we apply it in a certain way. Okay, now with this, right, we are interested in the coefficient of linear expansion. This, we call this the coefficient of linear expansion. Okay, now with this, the first thing we can do here, right, we can substitute this into this. Okay, we can substitute this into this. So in doing that, we'll arrive at the equation, and then after substituting, we can make alpha the subject. We can make the coefficient of linear expansion the subject. So in doing that, we'll get this equal to, so substituting equation 3 into equation 1, we arrive at coefficient of linear expansion multiplied by the length. We can put this into brackets, the temperature. Okay, so we replace this anywhere we see this here, then we'll get this equation. Now we can make this the subject, we can make linear expansion the subject. So in doing that, we arrive at this, right, changing the L on L naught times 1 on T. But mind you, we substituted this into this, right? So in replacing it, we have change in L on L naught times 1 on T minus T naught, right? Okay, so from here, when we make this the subject, we'll arrive here. When we also we substitute it into this, right? Everywhere we see this, we put in equation 2. We will get this equation. Okay, so now there's the equation that we'll be using for experiments. Okay, so there's the equation for the experiment. Now, the book says that we should plot the change in L against T, the temperature. Okay, we are plotting change in L against T, the temperature. Okay, so in doing that, we need to make L the subject, change in L the subject, not L naught. Now, mind you, we know the value of L naught. Okay, so in making this the subject, we'll arrive at change in L equal to coefficient of linear expansion and then T minus T naught. Okay, and then if you are confused about how this one came about, this is the same as change in L on L naught time change in T. Okay, so this is the same as this, right? If we want to factorize out change in T to become 1 on change in T so that L naught can, so this is the same as this. Okay, so in making this the subject, you get something like this. Mind you, our factorization tells us that this is equal to this. Okay, so this now becomes our equation. Okay, and then what we do next here is to expand. So our change in L equals to coefficient of linear expansion L naught, the T, minus coefficient of linear expansion L naught, and then T naught. But we are interested in only plotting this on the ordinate against this on the abscissor. Okay, so in doing that, we can compare to equation of a straight line y equals to ms plus c, and then we'll have our y component to be change in L, our s component to be our T, our gradient or our slope should be equal to coefficient of linear expansion and then L naught, and then our intercept should be our negative coefficient of linear expansion L naught and then our T naught. Okay, so when we are supposed to plot this against this becomes our y, this is our x, this is our x, this is our slope, our gradient, this is our intercept. Now, with doing this, we are expected to get a graph Let me rewrite the equation here. So we'll have change in L equals to linear L naught our T minus L naught T naught. So this is our Y, this is our X, this is our gradient. Okay, so our graph is supposed to look something like this, where this should be our T degrees Celsius, right? And then this is supposed to be our change in L in mm, right? So we have a graph like this. It doesn't go through the origin, mind you. So the graph looks something like this. Okay. Now after finding our slope, we can find our slope to be our change in L on mm on our change in T, right? Now we can come and equate our slope, because we said from here we understood from here that our slope or our gradient equals to change in coefficient of linear expansion times the L naught. Okay, so our slope, the answer, so after that you find the slope after plotting the graph, right? You find your slope, right? After finding your slope, you come and equate the answer of your slope. Answer of your slope to, we said, equals to L naught times coefficient of linear expansion. Mind you, we are interested in finding coefficient of linear expansion. So in doing that, we can have coefficient of linear expansion to be, by making this the subject, to be our slope. So we divide this side by L naught, both sides, slope on L naught. Okay, so that's how we find our coefficients of linear expansion after plotting our change in length of the metal against the temperature, which is proportional according to Charles' law. Okay, now there's a question here that we can look at. There's a question here, you see. So we are supposed to plot our change in L against T, and then we find the slope. So you know how to find the slope. After that, we have to use the slope to calculate the coefficient of linear expansion. See, the temperature coefficient or coefficient of linear expansion. We calculate it, which is the alpha. Okay, we know how to do that. We just did it. Now this question, let's look at how we do this question. It says that what is the length of the material tube at 80? Okay, at 80 degrees, right? So after finding our coefficient of linear expansion or our temperature coefficient, okay, of the metal, which is the same as coefficient of linear expansion. Now mind you, we know L naught already. Okay, L naught is 600 mm. So L naught equals to 600 mm. So we know this from our slope. We know this. We can just find this. Okay. So the next thing is, in tackling this question, this particular question, right? In tackling this question, what we do is we go back to the intercept, right? On the graph, there's an intercept here, right? Now, from what we did here, from our equation here, we said that the whole of this is our intercept. Our C equals to minus this L naught and T naught. Okay. So all we need to do is to substitute the values in here, then we can answer this question. It's very simple. Okay. So we have T naught to be 80. So let me do that here. So our C equals to negative this T naught. Now this is the value of the intercept. So our intercept equals to this L naught on T naught. So the next thing we do is we know this from the graph. Okay, we read the graph, we read this value, right? We know this from the graph. We know this from the graph. We know this from here, right? We just found it from here. Coefficient of linear expansion using the slope. We know L naught, right? So we can find the value of change in L at 80. Okay, we can find the value of change in L at 80. So with that, we come to this part. Okay, we use this particular equation. They say what is the length of the material tube, right? So we know this, we know this, we know this. Let's read the question again. What is the length of the material tube at 80? So now we are interested in finding L naught. So we are no more using this L naught. Okay, so using the intercept, the value of the intercept, we are finding L naught. So we divide this side by, we just quote this part of the equation, right? We quote this part of the equation as this, right, as our intercept. Then with that, we can make L0 the subject, where we'll divide this side by this and this, right? So this becomes our intercept on our this coefficient of linear expansion times the temperature. So we are interested in finding this. So we are supposed to find L0 for this question, right? Which is no more 600. It said at 80, what will be the L? Okay, so this is how you do it. The value of the intercept divided by this on this coefficient of linear expansion times the 80. We know this from the graph. We know this from the question, which is 80. We know this from the slope. After finding the slope, we found this, right? So now we can just compute for this. Thank you.